Hey guys, in this video we're going to talk about periodic trends. Now I know we're skipping around the notes a little bit, but I'm going to go through this before we go back to the photoelectron spectroscopy. So before we actually dive into the individual periodic trends, I need to introduce a concept before that. And so this is just the general idea of the periodic trends, what exactly is happening. So first thing I need to introduce is something known as Coulombs Law. Now, those of you who might have had physics before, you understand what Coulombs Law is, and you understand a little bit deeper than what we're going to have to go into for chemistry. But if you haven't had physics, or if you haven't heard of Coulombs Law, let me explain to you a little bit about what it is. Coulombs Law is the force of attraction between any two things. Okay, so this FATT, that stands for force of attraction. Now, the way that I calculate the force of attraction is Q1 times Q2. Both of those stand for charge. Okay, these things can both be positively charged. It can be positive and negative. It can both be negative, right? But it's just two things that are charged. Okay, and you take that value and then you divide by your r squared. Now, r stands for the distance between those two things. So r radius, distance between the two objects that are charged. Okay, so I can measure the force of attraction. Now, let's think about that conceptually. If I have something that has a great force of attraction, then that means it's going to be hard to rip it apart, right? So just keep that in mind. If I have something that is a small force of attraction, not a very large force of attraction, I can take those apart very easily. So that idea is going to help us a little bit in one of our periodic trends. Now that we understand Coulomb's law, let's talk about the relationship between each of these things, okay? Now, if I were to increase the charge of something, so if I were to increase the charge, then what that does is it increases the force of attraction. If I increase the force of attraction, a couple of things could happen. Well, I can make things smaller because it's held more tightly, or it's harder to remove something, right? So this is going to translate to our periodic trends. If, however, I keep the same charge, but instead I want to compare my distance and my force of attraction. If I increase the distance between these two things that are charged, then what happens is my force of attraction decreases. So it's held less tightly, or it's easier to remove something from that. So how does Coulomb's law, how does that translate to the periodic table? Well, anytime I'm moving across the periodic table, so let's say I'm going from hydrogen to helium, or I'm going from lithium to oxygen or something. I'm going across the periodic table only, not diagonal, just across. What's happening there is you have the same energy levels. So basically this distance right here is staying the same. Right? Your distance from your valence electrons to your nucleus is the distance that we're talking about here. Valence electrons, meaning outermost electrons, to my nucleus, which is positively charged. So as I'm moving across the periodic table, I have more protons that are embedded into my nucleus. So more protons added, more protons added. What that is doing is that is increasing the charge that I have there. So it's increasing the charge. Now, what we call that is ZEFF, Z-E-F-F. And what that stands for is effective nuclear charge. All right, just think about that name, effective nuclear charge. So it's how effective that nucleus is charged, how effective it is to holding electrons in that atom. All right, so if my ZEFF increases, what happens to my force of attraction? Well, it increases as well. So this is a main idea anytime you're going across the periodic table. Now, let's talk about what happens as I go down the periodic table. As I go down the periodic table, what I'm doing is I'm adding energy levels. So I have one energy level, then the second row I have two energy levels, then three. So what's happening to the distance between my nucleus and my valence electrons? Well, that distance is increasing as you are going down the periodic table. And if that distance, right here in our Coulomb's law equation, if that distance increases, then my force of attraction decreases. So a couple of things are happening there. Now that we understand this idea, you do have to talk about this stuff in your essay type questions for free response. Let's apply this knowledge to our periodic trends. So the first periodic trend we're going to talk about is atomic radius. So let me scroll down here a little bit. Or let me see if I can find a place to be able to scroll down. Ooh, scroll too much. Yeah. All right, where are we at? We are here. Okay, atomic radius. Now, if you did the inquiry like you were supposed to, what you saw as you go across the periodic table is that the atomic radius decreases. So as you go across the periodic table, let me get my pen again, the atomic radius decreases. As you go down the periodic table, our atomic radius increases. All right. Now, not only do you have to know the trend, but you have to explain why. All right. So why is it that the atomic radius decreases as you go left to right? Well, here's what's happening. Go back up to where we talked about across the periodic table. As I move across the periodic table, I get more protons in that nucleus. More protons in that nucleus increases Zeph, which stands for effective nuclear charge. And if I increase Zeph, what does that do to my force of attraction? That increases my force of attraction. So now, if I'm tightly attracted, if I have a large force of attraction, that means that those electrons are held together pretty tightly. All right, and if my electrons are held together more tightly, then that's going to make a smaller radius. So that is our justification as to why atomic radius decreases as we go across the periodic table. Now let's focus on the down portion. As we go down the periodic table, our atomic radius increases. Now we have to understand why. The reason why is as I go down the periodic table, I'm adding energy levels. So because I'm adding energy levels, I'm increasing the distance between the nucleus and the valence electrons. Well, if I increase that distance between the valence electrons and the nucleus, what happens to my force of attraction? It goes down. If my force of attraction goes down, are my electrons held as tightly? The answer is no. So if my electrons are held less tightly, guess what? I have a bigger atomic radius. Atomic radius is just transferring to the size of the atom there. Now, not only do you have atomic radius, but you have ionic radius. So let me explain what the difference is between the two. An atom is neutral. It has all of its protons and electrons. They're equal. But ionic radius is of an ion. And what is an ion? An ion either loses or gains a certain number of electrons. So you need to know what happens when cations are made. Cations are your positively charged things, your positively charged ions. And cations are made by losing electrons. Now, let's think about it. What will happen to a cation? What will happen compared to the regular atomic radius to the new radius? So, if I have my regular radius and then I have my cation, which means I've lost an electron, we've got to look at the ratio of protons to electrons. If I have a neutral atom, then I have the same number of protons and electrons. But if I now take away an electron, I have more protons than electrons, right? So if I lose electrons, I now have more protons than electrons. And remember that those protons are what we have for that effective nuclear charge, right? If we have more protons, then guess what? My force of attraction is held more tightly. It's greater. So if my force of attraction is greater, that ion, all those electrons are held more tightly. Therefore, cations are smaller than the neutral atom. Okay, so I'll say that again. Cations are smaller than the neutral atom. We have to justify why. Well, the reason why, I'm losing electrons, so that means I have more protons than electrons. If I have more protons than electrons, my force of attraction increases. And if my force of attraction increases, those electrons are held more tightly. Therefore, you get a smaller ionic radius. Now, let's talk about the opposite. Let's talk about anions. What's happening to anions? So first of all, what is an anion? An anion are your negatively charged ions. Okay, so what is happening there? Well, when I have a negative charge, that means that I have gained electrons. Your anions gain electrons. Now, what's the deal there now? If it was neutral, same amount of protons as electrons, right? But now it's no longer neutral. I have more electrons. Is that nucleus as effective holding all these guys together? No. So therefore, your force of attraction goes down. And if your force of attraction goes down, what does that say about its size? It gets bigger. So anions are larger than the neutral atom. The reason why? Since it gains electrons, it now has more electrons than protons, which decreases your force of attraction. Therefore, those electrons are held less tightly, which translates to a bigger size. So you will have to be able to discuss both atomic radius as well as ionic radius. The biggest thing is being able to explain these justifications. You always have to relate it back to that Coulombs Law, that force of attraction, what's happening there. So now let's transition to our other periodic trends. Ooh, hello, I'm up here at the left now. All right, so the next one we're going to talk about is ionization energy. So first we need to understand what ionization energy is. It's defined as the energy required to remove an electron. So we're going to take off an electron. Now, first of all, we need to understand what electron are we going to be taking off. We always take off our valence of electrons. And what does valence mean? Valence means outermost electrons. Okay, so the outermost shell, those outermost electrons go first. You'll see on for your response that you have something called like first ionization energy, second ionization energy, so on and therefore. What that means is the first ionization energy means that it removes its first valence electron. So we're taking away its first valence electron. A second ionization energy means now that I'm removing that second valence electron. So that first one's gone. Now I'm going to take away that second one. So it's just some terminology that you'll see there when you're answering some free response questions. Now let's figure out the trend, okay? And if you did the inquiry like you were supposed to, you should have found out that ionization energy increases as I go left to right and decreases as I go down. All right, so ionization energy decreases as I go down and increases as I go left or right. Now, not only do you need to know this trend, but you have to be able to explain why. And so this is the same idea as we talked about with atomic radius, but now we've got to talk about it in the form of energy. So as I go across, again, what is happening? As I go across the periodic table, you have more protons. More protons means that your Zeph, effective nuclear charge, increases. If your Zeph increases, what does that say about force of attraction? Well, your force of attraction increases. Now, think about it. If I want to remove an electron, I have something that is very tightly attracted, a large force of attraction. Is it going to require a lot of energy to remove an electron, that valence electron, or is it going to take a little bit? Well, hopefully you answered right. It's going to take a lot of energy to remove that valence electron. And that's what ionization energy is. So if my force of attraction goes up, then my ionization energy goes up as well. Therefore, that means more energy is required to remove the electron. Now let's talk about if we go down. Well, if we go down the periodic table, what's happening? The distance between the nucleus and the valence electrons has increased. What does that do to force of attraction? Well, if that distance has increased, my force of attraction goes down. And think about it. If my force of attraction goes down, those electrons are not very tightly held together. Is it going to take more energy or less energy to remove that electron? Well, hopefully you answered right. It's going to take less energy to remove that electron. So the idea here is that as force of attraction decreases, ionization energy decreases as well. Less energy is required to remove the electron. Now, I want to look at this data table here below, okay? And so you see that we have, maybe, let me see if I can blow it up a little bit. Give me just a second. Okay, so I blew it up a little bit. Hopefully you can see it okay. So let's look at that periodic trend as we're going here. So hydrogen to helium, what are we doing there? We're going across the periodic table. So what's happening? Zeph increases. So my force of attraction increases, so ionization energy increases. More energy is required to remove the electron, and our data is showing that. What we have here is first ionization energy. Remember that, it's removing the first electron, valence electron, I should say. And so it's increasing. Then I go to the second energy level. Well, if I go down an energy level, what's happening there? My radius, my distance from the nucleus to the valence electrons has increased. And if that increases, what happens to my force of attraction? It decreases. So therefore, since my force of attraction decreases, ionization energy decreases, which means less energy is required to remove the electron. Now, as I go to BE, you see how I'm going across the periodic table again. So force of attraction increases, ionization energy increases. Now, BE to B, that's still going across the periodic table, right? But instead of it increasing, it's actually decreasing in ionization energy. This guy right there is known as an exception, all right? So there are some exceptions to these periodic trends that we have to be able to talk about. And they love to ask about them. So BE to B is one exception. And we'll see that there's another thing that follows in this line as well. We're going to call that exception number 1. So I go to boron, go to carbon, increasing ionization energy, nitrogen, increasing ionization energy. Oh, wait a minute. Nitrogen to oxygen is also going across the periodic table, but what do we see? Instead of the trend that is supposed to increase, then we actually see it decreasing. So this is another exception we have to talk about. Nitrogen to oxygen. Then we go to fluorine, then we go to neon, all right? And then we go back down another energy level. So sodium to magnesium, okay, that's following the trend. Magnesium to aluminum. Oh, wait, that does not follow the trend. But if you compare these two transitions on the periodic table, you'll notice something special about them. BE to B is going from the S to the P. It's jumping over the D's. From MG to AL, that's also the S jumping over to the P. So something is happening there. So BE and B and MG and AL, they both follow the same rule of exception. Now let's keep going. We keep going, keep increasing. P to S, that's also an exception, right? Now, let's compare these two things on the periodic table. Nitrogen to oxygen, and then you have phosphorus to sulfur. Guess what? They're right underneath each other. So something's happening there. So we're also going to talk about this guy being an exception as well. We go, therefore, what do you notice is happening here? Here we have our D block, right? So our D block we still have a slight increase in ionization energy as you're going across, but they're all relatively the same. You don't have as much of an increase of an increase of that ionization energy as you go. So as you get to your D block, those are most closely related as far as ionization energy goes. All right, so let's focus on these exceptions, okay? If you look at the periodic table, let me pause you and get you a periodic table here. All right, so here's our periodic table. We have B, E to B, and we have Mg to Al, okay? We're going to call this exception number 1. Now, here's what's supposed to happen, right? We're supposed to have an increase in ionization energy, but that data table right there told us that there wasn't an increase in ionization energy. Instead, it decreases. So it has something to do with the S transitioning to the P. All right. Now, this is a horrible analogy I give, but it works. Some people say that they can visualize this or whatever. Okay. So let's say an S electron is a very good child. Okay. So this poor single mom's going out shopping, right? Going to Target or something. And she has 2 kids. Okay. One kid is an S electron. The S electron is very well-mannered, not much energy, just kind of sticks close to its mom. Okay, good kid. I hope my child's like that if I ever have kids. The second child, however, is a P electron, right? So this is my S electron to my P electron. My P electron is this crazy kid jacked up on some Mountain Dew. So just think about like running around everywhere, getting everywhere, not sticking close to the mom and things like that. Okay. So this is horrible. Ionization energy. Think of it as like this kidnapper guy. Okay, so he's prowling the target area. Okay, and so he sees these kids, right? He has the S electron, which is close to the mom, well-mannered, not much energy. This P electron, which has tons of energy, not as close to the mom, just kind of going everywhere, jacked up on some Mountain Dew. Which kid is it going to be easier to grab? Which requires less energy to grab? Well, it's going to be that P electron. He's going to be snatched. Okay, now, why is that? This P electron already has a lot of energy. So not much more energy needs to be put in order to take away that electron. So here's what we need to talk about as our exception. S electrons are lower in energy than P electrons. I hope you're writing this down. I'm not going to write it down. I'm just going to talk slow. So S electrons are lower in energy than P electrons. Therefore, less energy is required to remove a P electron than an S. And I also always have to bring it back to the trend. We know that this is an exception, so you want to add to that, despite the increase in Zeph. So yes, my effective nuclear charge, my Zeph is still increasing. Therefore, my force of attraction should still increase. However, because that P electron, just that first P electron, since it has very high energy, it's going to require less energy to remove it. And that's why your ionization energy decreases for this exception. And it only works from BE to B or Mg to Al. So I hope that is a little bit understanding, and I apologize for the horrible analogy. Now let's talk about our second analogy. Our second analogy, let me get a thing that can look better. So N to O and P to S. All right, so that is our second exception there. Now for this, I have to draw a little bit of a picture, okay? Let's do the orbital notation. I'm going to draw it up in this area here. Let's do the orbital notation for nitrogen. So it is, we're just going to do for the P block, all right? So it's in the 2p. And nitrogen is 1, 2, 3. So 1 electron, 2 electron, 3 electrons. So this is for nitrogen. Now let's also do the same thing for oxygen. So oxygen is 1, 2, 3, 4 electrons in the 2p block. So there's 2p, 4 electrons. So 1, 2, 3, 4. What do you notice is the difference here? This p block for nitrogen has all unpaired electrons, right? This oxygen, however, has what we call a first pairing of electrons. So let's think about what happens when two electrons come together. This guy's negative, this guy's negative too. Well, you have two negatives, don't make a positive, right? So instead they're going to repel each other. Now, this is called electron-electron repulsion. That's bad. That's very bad, okay? Electron-electron repulsion means that nucleus, which is trying to hold that electron in, well, if that electron's being repelled, it's kind of, obstructing what that nucleus is supposed to be doing, which is holding this stuff together, right? So if I have my first pairing of electrons, this electron-electron repulsion, that valence electron there is going to require less energy to remove it because it's being repelled. It's going away from the attraction of that nucleus. So again, what we say for this is in oxygen, we have the first pairing of electrons, which creates electron-electron repulsion, therefore requires less energy to remove that electron. And we know that this is an exception to what's supposed to happen, so we say despite the increase in Zeph. So that is letting the AP reader that you know that this is an exception to the trend. So this is how we do the nitrogen to oxygen exception as well as the phosphorus to sulfur exception. And if you need me to actually write these out, then I can. Hopefully you got it pretty well. We'll talk about it in class if we need to, if you have any questions. So those are the exceptions to the ionization energy trend. Okay, make sure you know how to explain this stuff. Okay, if you don't use the correct terminology, if you don't use the correct keywords, here comes Kamala again, then you will not get full credit. And it is so easy to get credit here as long as you follow a correct chain of events and just put it into a paragraph form. Okay, there's one more thing we need to talk about before we leave. So give me a second to get set up. All right, this last thing that we need to talk about is electron affinity. Now, electron affinity, Kamala's going to help us teach, has the same trend as ionization energy. So first we need to define what electron affinity is. Electron affinity, if I have an affinity of something, you all probably know this. I have an affinity for Iron Man. So what does that mean? I love Iron Man. I like it. I have a liking to it, right? So if I have an electron affinity, then that means you like electrons, so you want to pull them to you. This is a little bit different from electronegativity. What electronegativity is the attraction or the pulling of electrons when it's in a bond. So we might touch on electronegativity a little bit in this unit, but really it will come across in bonding, which is next unit, because electronegativity is what's happening when you have a bond. And this is atomic structure, and we're not working with bonds yet, so we're building on top of that. So instead, electron affinity is just the liking of electrons. You like to attract the electrons to yourself. So it's increasing as you go across the periodic table, and it decreases as you go down the periodic table. All right, why is that? What's our justification if we ever have to talk about this? Well, the same thing as the ionization energy. You go across the periodic table, more protons, which increases Zeph. Therefore, it increases force of attraction. So if I have a greater force of attraction, hey, I want more electrons coming closer to me, right? So that's what's happening with electron affinity. If I'm going down on the periodic table, all right, what's happening there is your distance between the nucleus and the valence electrons are increasing. Well, if that distance is increasing, force of attraction goes down. If force of attraction goes down, then I'm barely holding on to the electrons that I have already, right? I don't want more. So you don't have a very large electron affinity. All right. You don't tend to talk about electron affinity as much as ionization energy, atomic and ionic radius, but it is a thing that you need to be aware of. And if they want to throw it at you, you'll be able to hit that curveball out of the park. I'm sorry I'm being quirky today. I'm sick. And so I'm sorry. Anyway, that's it for this video. I think we have one more video on this unit, and that is photoelectron spectroscopy, which is super easy if you know how to do electron configurations. So I'll catch you on the flip side.